Okay, so let me give you another example of arrival times by absorption. In this case, the absorbing point is at infinity. Now, that is maybe not a very practical thing, but you could think of idealizations of this, think of this as an idealization of a situation where the particle really travels far out and very fast. So here is the Hamiltonian for this. So you take a standard kinetic energy, let's put the mass to be 1/2 so that we don't have to write the 2m. And my potential is the function of the position, right? So this is just a standard Schrödinger operator, but it's a cubic potential. Right? So nothing fancy really, but this thing has a problem. And so classically, of course, you could look at this as a classical Hamiltonian problem. So classically, if you just compute how long it takes for the particle to get far out, you get an integral over the velocity, right? So that's a standard thing in classical mechanics, and then actually this integral converges as the space where the point where you look goes to infinity. So actually, there's escape to infinity. Infinite time. And quantumly, this also is sick, right? So um, this is not essentially self-adjoint on its natural domain, let's say on Schwartz functions. You pick some natural dense set of nice wave functions for which you can apply P and Q in arbitrary powers. That's basically the Schwartz space. So that would be the natural domain of an operator like that. And then it turns out that this guy is symmetric. It's a Hermitian operator, so the scalar products satisfy the usual reality relation, but it's not self-adjoint, which means that H star psi equal I psi, well, actually also the opposite sign, has solutions, right? So that is if you look at the definition of the adjoint for unbounded operators, that just means this kind of psi would have the property that psi h phi is equal to, well, whatever, plus minus I psi phi. So this is sort of under a scalar product where you have something with phi in the domain of k, in the domain of h, right? So you can find vectors that have this property. So that would be eigenvalues of the adjoint for an imaginary eigenvalue. And that is the hallmark of something not being self-adjoint. Right? So for a self-adjoint operator, this cannot happen. You don't find such solutions except psi equals 0. Right? So these are called defect solutions in von Neumann's theory of self-adjoint extensions, which he did in 29 or so. So this means that you cannot exponentiate, right? So e to the I minus I th is not defined. And if you bring these two together, that is actually something you should almost expect, because if you write a Hamiltonian time evolution, this automatically goes for all times. It goes on forever, right? So you can arbitrarily large times are included, which is not the case in the classical problem, because at some point the particle is gone, right? So this is classically you can have situations where you have incomplete dynamics in some sense, or where the particle can escape the region that you that you're considering. In quantum mechanics, we don't usually allow ourselves this liberty, right? So this freedom. If you look at dynamics that are not globally defined, right? So that way you would have some kind of escape phenomenon like that. Okay, so also von Neumann's theory tells you how to deal with that. You can make a self-adjoint operator out of this by combining these defect solutions and define a domain for an operator that is then self-adjoint. So this is actually the core of von Neumann's theory. And you can also do this classically. What this amounts to, classically, you would have the particle going off to infinity in finite time, and of course it becomes infinitely fast, right? This is a driving away much worse than an oscillator. So it has infinite speed, hits infinity with infinite speed. And then you sort of can make a reflection at that moment and shoot it back also with infinite initial speed. I mean, under conservation of energy. And then it comes back, and of course it will run into the potential looks like that now, right? It will run to the potential um, hill here, and will be reflected, and then dash off to infinity. So this will become a periodic thing, right? Um, Not very physical, actually. So depending on the situation that we really want to describe, which is never something with infinity, but some idealization of infinity, right? But it would be a case where the stuff that you forget because it's so far away comes back with a vengeance, right? So this is the kind of modified dynamics that would describe that you have in that case. So using a self-adjoint extension in this situation for this quantum Hamiltonian, the same thing would happen, right? So you're basically, I mean, conceptually, you're doing pretty much the same thing. The stuff gets reflected at infinity and shot back. And because classically you have a periodic evolution, you expect such Hamiltonians, which you can define, right? There's actually a one parameter family, so there's these the dimension of these spaces that of the space of psi's that satisfy these for plus I and for minus I are one. So the defect indices are 1, 1. That's the terminology here. That means you have a one parameter family of extensions. Okay, you just do that and compute the what kind of spectrum you get. And you will not be surprised to hear that you will get discrete spectrum, which is related to such a periodic thing. Right? So that's one way out of the ill-definedness of this quantum operator. Make it Hamiltonian, make it a self-adjoint Hamiltonian. But that means that you do this artificial bounce at infinity. So classically, actually, you don't care. There's no problem in defining a time evolution where the particle just goes away, and if it's gone, let it remain gone. Can you do that also? Well, von Neumann's theory tells you that you can also make dissipative extensions, as they're called. That is, you can make extensions that are contraction generators. So instead of choosing a self-adjoint extension, a self-adjoint extension, choose one that generates a contraction semigroup. So von Neumann's abstract theory also tells you that, how to do that, and how many there are, and so on. So there's some freedom in the choice there, and it's a bit unclear how to define that in general. In this case, basically, it amounts to saying we only allow the outgoing asymptotic solution in the game and don't consider the ingoing one. And that is a way to define the generator. There's also a more elaborate way. You do a path integral formulation here. Path integrals here would basically be given by the Trotter product formula. That is ill-convergent in this case. However, as there's one way to regularize the path integral, which is saying that the mass gets a small imaginary term of the right sign. Then everything becomes contraction semigroup. That was done by Edward Nelson in the 60s, I think, pretty early. Right? So this is one interpretation of path integrals that actually work. Then normally, if you have a nice potential and you take the mass, the imaginary part of the mass to zero, you get back your nice Hamiltonian, right? That's a way to regularize path integrals, even though literally they may be not directly well defined, right? So that's Nelson's way of doing it. Now, for a nice potential, that gives you back a unitary evolution. For this potential, actually, you pick out one particular contraction semigroup that does that. So do the path integral, take Nelson's regularization, take the limit of the mass going to the imaginary part of the mass going to zero, then you will get one particular contraction semigroup that I roughly described with focus on the outgoing wave. And this is a perfectly good time evolution for quantum systems, right? So the time observable that you get with this, the arrival time observable, is the arrival at infinity. No problem, right? And there's nothing wrong with this kind of dynamics, and you don't force yourself to artificially introduce a reflection at infinity, which actually will come back in a finite time to you, right? And you're not maybe you're not interested in that effect, right? So I'm just advocating here that you take contraction semigroups as a natural setting also for incomplete dynamics or for dynamics in cases where there might be an escape to infinity. Okay. Okay, so I would like to add a brief remark connected to something that you maybe know, which is the generators of completely positive semigroups that are usually written in the Lindblad form. And so, as you know, probably when you have a semigroup of completely positive maps, its generator, and the generator happens to be bounded, which is actually very rare, but if it happens to be bounded, then it has this particular form of a Lindblad generator. So that is, if you apply it to a density operator, I'm writing this in the Schrödinger picture. So then this is like minus I k plus I rho k. That is something. Maybe I should have an h bar here. H bar is 1 now, right? Okay. And then you have a sum of jump terms. So sum L alpha, rho L alpha star, something like that, right? And if the overall generator, if this is a bounded operator on the trace class, then all these are going to be bounded operators, and this is a theorem by Gorini, Kosakowski, Sudarshan, and Lindblad. Right? So well-known traditional result. Now, in quantum optics, typically these guys are creation and annihilation operators. This would be quadratic in them. So these are unbounded operators. And it's not so clear what in that case actually should a Lindblad evolution should be, right? So, sorry, I should put a star here. Um, so actually, I would like to connect this to the arrival time problem and to show that all the unboundedness that you may have in such an operator, and the typical ones in quantum optics definitely meet that description, that just comes from an arrival process. And so, so the arrival time is connected with what Brian Davies calls the no event semigroup, which would be like, again, like Ct as e to the minus I tk over h bar, and that's where this minus I comes from, and I'm forgetting h bar is 1 now. Right? So so in the context of the Lindblad game, this is called the no-event semigroup, and it's actually contraction semigroup on the Hilbert space. So this is like when the trace glass has d square dimensions, that has only d dimensions. So it's always a good thing to do something on the wave function level rather than at the density operator level, which is like many more parameters and the complexity that goes with that. So this is actually a nice thing to have. Now, this hasn't. So think of this as, first of all, at the whole process that you look at, as something with an arrival time here. So then you can form E, it would be the exit space of that, right? That, even if that is an unbounded generator now, you could think of the exit space. And this describes the state, if you want, upon arrival. So how do I get from there? I'm not just interested in this first event that happens, right? So the first arrival, but I want the system to survive. So so compose this with a channel that takes that takes the state upon arrival. That is a density operator on E to system state. So you're reinserting the system. So this would naturally be called reinsertion. And this will have some cross operators. So the state upon arrival, the arrival state somehow, let's say rho E, right, gets mapped to, well, we know how completely positive operators look like. So this is something, some sum over R alpha rho E R alpha star, where these R alpha now are maps from the systems, from the space of the input systems, that is E, into the Hilbert space H of the system, right? And they're bounded up. This is a standard Krauss representation. So this reinsertion map is a bounded operator. The generator of the contraction semigroup may be unbounded, but on the exit space, this guy is bounded. And so I won't go through details, there's a lot to tell about this, but I just want to say that the way to understand a Lindblad operator with unbounded, which is unbounded, right? The generator is unbounded, and this covers practically everything you do in quantum optics, this form, then you describe the contraction part in the way that I told you. There will be some exit space, and then you take just the reinsertion, and then the system survives, because then you're measuring something upon first arrival, but this has now has become a system state. These R alpha basically composed, so R alpha composed with J are the jump operators. And now this is a rough formula, but if you write it down carefully, you'll see that if J, for example, you have absorption at a boundary, then these are not good operators, right? So like the delta function potential is not an operator in itself. So actually, it can happen that in this way you have perfectly well defined Lindblad evolutions, where dl alpha star isn't actually defined as it is normally defined for an operator. It's not a closable operator. It really, the formula doesn't make sense like that. it does make sense when you apply it to ket bras in the domain of K, and then the alpha would be pull that in, and you don't need to have it actually literally have the star defined there, right? So that's how you interpret this. So this has to be interpreted with some care, but that is automatically done if you have this understanding of the Lindblad operators. So if you want unbounded Lindblad operators, think exit space and reinsertion. That is my message here. Now, it's unfortunately not true that this covers all generators of completely positive semigroups that are strongly continuous on the trace class, let's say, right? So that you can even talk about a generator. And so there's a paper by Hollywood from the late 90s where he shows that there are non-standard CP evolutions, and they would have different generators. You cannot always use this trick. But this unbounded Lindblad form that I've just roughly described here does cover everything you write down in quantum optics typically. It's an interesting question what else you can have. There's also interesting work by Bill Alberson on other generators. And I don't know where they can be used. I suspect yes, in field theory, for example, but that's a matter of current research. Okay. So we saw that for covariant arrival times, there is just a standard uncertainty relation for the variances of the arrival time distribution and of course, the distribution of the energy. Now, in the absorptive case, this is not so obvious that anything like that should be true. Actually, in order to define the absorptive arrival time, we mess up the Hamiltonian. We change that to this contraction generator. So the distribution depends on this way we do that. So why should the original energy satisfy any relation with this guy? So actually, some time ago, I gave a lecture together. So we took turns. We gave a lecture together with Andreas Ruschhaupt at the University of Hanover at the time. The lecture was The Quantum Mechanics of Time. And so I remember we were discussing this problem. Could there be an uncertainty relation over lunch? And so we made a scientific bet, and I'd like to do that. I have a bad reputation for winning them, but in this case I was pretty sure I would lose it, namely betting that there would be something like an uncertainty relation here. And Andreas was holding against it. So we thought about it a bit more, and then it turns out I won the bet after all. So so there will be a condition, though, that you need to satisfy that makes this connection. So of course, they have to be related somehow. So actually, this is the uncertainty. So the absorptive arrival time, so delta t, would be the variance, well, the root variance of the arrival time. And of course, this depends on k, right? And how the k was the contraction generator, and of course, it anyhow depends on initial state. And both will depend on the initial state. And so delta E is the root variance energy distribution. So that depends on the system Hamiltonian, right? And now also one special case here of a arrival time would be one where the absorption is very weak and actually most of the particles don't even get detected. So you have to be careful about what you say about variances of a distribution, which is conditional on the thing even being absorbed. If it's not even ever detected, then of course then this quantity doesn't have to tell you so much. Right? So then the conditions that we have are that the psi is the initial state here, And we want this to be in the domain of the Hamiltonian. That's reasonable if you want to compute the bands anyhow. And also in the domain of this other guy. Actually, we need a little bit more. And the crucial condition here is that both these expressions, h psi, and this expression make sense. So remember, we had some of the possible K's here were h with an addition of an absorbing term. So this is just saying the absorbing term vanishes on the initial state. So you could say, do not start inside the detector. That would be a colloquial way of saying this. So the absorbing terms vanish at on the initial state, or these operators are the same. And then we need something more. So P is the total absorption probability. Total absorption probability from psi. By, of course, by this absorbing process, right? So actually, if that's zero, we'll see that if the things get never absorbed, you don't learn anything about the distribution of the arrival time. So the relation will be trivial. So then actually we have that delta t times delta E is larger than, well, square root of P times h bar over 2. The last bit you know, right? This is what you have for all these kind of uncertainty relations. But so this factor comes in because we are looking at a distribution conditional on arrival. And so this is the way it plays out. So we have a paper on that, actually, together with an experimentalist, Pete Schmidt, who made a proposal of how one could measure this in a quantum optics setting. So yes, so the uncertainty relation also holds for this case, maybe somewhat unexpectedly.